Hi, my name is Stuart Ozer, and this is Lab 5, Magnetic Braking with Faraday's Law. The purpose of this lab is to explore the interaction between the falling magnet and the tube of aluminum foil. We use equations such as Faraday's Law, Newton's second law for falling magnet calculations, the Biot-Savart law for current calculations, and Newton's third law for falling magnet calculations. The initial conditions were the setup of the experiment in terms of what the tube looked like. So we had a length of 0.4572 meters, a foil width of 0.00254 meters, a magnet dipole of 0.37642, a magnet mass of 0.0241 kilograms, and an inner radius of 0.01397 meters. The system was the magnet and the tube, and the surroundings was everything else. The main result preview, we have a computational model predicted a 0.297 second drop, and the real-life experiment determined a 1.176 average drop. We'll get into why this might have been later. The experiment, the bar magnet was dropped down a tube of aluminum foil, and this was repeated 10 times. A stopwatch measured the entrance to the exit time, and then the overall average time was calculated. The computational model was then run. So for the trials, from 1 to 10, we have 1.21 seconds, 1.36 seconds, 1.16 seconds, 1.06 seconds, 1.21 seconds, 1.23 seconds, 1.13 seconds, 1.23 seconds, and 1.13 seconds, and then 1.04 seconds, with an average time of 1.176 seconds. So in my computational model, I developed two functions here. We have dipole B and calculate d flux dt analytic. And so dipole B calculates the magnitude of the magnetic field. And we see there, we get return B right there with Biot-Savart's law is mu 0 over 4 pi times 3 times the dot product of mu and r hat times r hat minus mu over r mag to the third power. So that calculates the vector B, which is the magnetic field. And then d flux dt analytic calculates, d flux over dt. And so we have the radius of the ring is the radius of the ring. The distance is the absolute value of the distance between the bar and the ring. The speed is the magnitude of the bar's velocity. And so then in the numerator, we have 3/2 of mu 0 over 4 pi times 4 pi, so that we just get mu 0, times the magnitude of mu, times distance, times speed that we calculated earlier, times the radius of the ring squared. And so then we get the denominator is the square root of the radius of the ring squared plus the distance squared, all to the 5th power. And then the df dt is the numerator that we made over the denominator that we made, and then we return that value. So then the force of gravity is negative mg in the y-hat direction. And then we calculate the current to be, using Faraday's law, to be negative d flux of dt over the ring.r. And then we find the field at the location using dipole B, take the hat of that vector, find the angle between mu and our magnetic field, and then we calculate the force on the ring, 2 pi, which is the absolute value of 2 pi times the current times the radius times the magnitude of B times the sine theta. And then we take the magnitude of the force on the magnet, and we add to it the magnitude of the force on ring and reassign it back to the magnitude of the force on magnet. And then we say that the F magnetic is positive magnitude of F on magnet in the y-hat direction, and then we add that to F gravity to get the net force. We predicted a 0.297 second drop. The real-life experiment determined a 1.176 second average drop. So the sources of error here were likely computational errors or human reaction time. It's definitely somewhat human reaction time, but it's also possibly computational errors since that difference is so large, and the baseline drop of the magnet itself was 0.31 seconds. So this has to be some computational error. For the questions, we've got, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, the current would need to increase, and so the magnet would fall for longer. And then what if the holes or slots were cut into the tube, how would this affect the ring currents in your model? Well, it would decrease the magnetic force because now there's less tube, and so the magnet would fall faster. Thank you.